Good morning, guys. So today we are going to let you about the Lewis dot structure of the atoms. This video is continuation with the previous one for the chemical bonding part 1. So in this video, we will talk about different concepts. First, I will start with the Lewis dot structure of the atom. So Lewis has given a very important part that every atom, they combine with each other to get stable electronic configuration. They can either transfer the electron, they can share the electron, or they can just give the electron, take the electron and transfer or share the electrons. So for that, they just want to obtain 8 electron in their outermost shell because octet rule said that atom to be get stability, it should have 8 electron. It sits in its outermost shell. But there are some exceptions are also there, like in case of hydrogen, if I'll say atomic number 1, but 1. So he has to take 1 electron to get stabilized. Or because I'll let you know why. Because according to the rule, the nucleus, there are K shell, L shell, M and O P like this. So in the cave, the first shell only contained 2 electrons, then 8, then 18, then 32, then 50 and 70. As the number of, you can say, as the number of shells increases, number of electrons will be increases as their electron capacity will also increases. So we will say that electron they just combine to get the noble gas configuration, or they can be stabilized like a octet rule. So in Lewis symbols, what happens? We call also then that a dot structure. So basically, what is the rule of writing the Lewis dot symbols? First, here you have to just know about the atomic number. Suppose in case of lithium, what is the atomic number of lithium? Hydrogen, helium, lithium, 3. According to the octet rule, we can write it like on configuration like 2, comma 1. So how many valence electrons are there? 1. So we will represent lithium as like this. In case of nitrogen, so if I'll take the example of suppose nitrogen, nitrogen is having atomic number 7. So in this case, atomic number 7 is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. So it can comma 2, comma 5. So nitrogen will have 5 electrons. But how will represent? In every direction, we will write first 1 electron. Then pairing will start. This is a rule. Okay. So in case of oxygen, 2, comma 6. So oxygen will be write like 1, 2, 3, 4, 5, and then 6. In case of fluorine, you will see 7 electrons. Like this neon, they have 10 electrons, 2, comma 8. So this is like something we can, use these Lewis symbol to represent the atoms or for their valence electrons. Okay. So can we write the Lewis symbol for ions? Yes, of course. Suppose in case of fluorine, they are having 7. But if it is taking 1 electron, so you have to represent like this. This electron will get pair up and we will write ki isne 1 electron. It is already taken up. So metals form cations and non-metals form anions to attain a stable valence electron structure. So we have seen in our previous video that in a periodic table, in the left side, you are having metal, and on the right side, you are having non-metals. And metals, they are forming cations because they are giving the electrons. They are not so much electronegative, but non-metals, they are very electronegative. So the stable structure often consists of 2 s and 6 p electrons. Okay, so now you can check here if it is a noble gas configuration. You can check this is 2 electron, 2, 4, 6, 8 electrons, like this 2, 4, 6, 8. So this is how the game begins. Like 1 electron. So this is some 20 elements. I have given the valence electron of. This is something that we are learning about the Lewis dot structure. So with the exception of helium, this structure consists of 8 electron in the outermost shell of the shell. Means this helium doesn't have 8 electrons. So this is the exception for the octet rule. Very simple. So if somebody is asking that can you draw the Lewis structure for carbon dioxide, that is CO2. You know what? Carbon is having 4 valence electrons. Okay, so I can write like 4 electrons, and oxygen is having 6 electron. 2 is here, then oxygen 2 electrons are there. So because it is having 6 electrons, there will be a bond formation like this. In case of O2, they will do like this. So it is something a sharing of electron. This is a Lewis dot structure for CO2. Now, if you want to draw the Lewis dot structure for the carbonate ions, then you can go for CO3 2 negative. So how this carbon is having 4 electrons? This is the one, say, second, third, and fourth. And all these oxygen, they are having 6 electrons. One oxygen will have 6 electrons. Okay, like this. So 6, it will, 1, 2, 3, 4, 5, 6. 6 is already there. And 1, 2, 3, 4, 5, 6 is already. 6 electron here, 6 electron here. But here 4 electrons. Why is it so? If 6 electrons they are having, so from where they are getting this one electron? This one electron and this one electron. So to understand this, you have to check 2 negative. 2 negative means they have already been getting 2 extra electrons. So these are these 2 electrons. Okay. So this is how we can understand. Now you can have the one glimpse of Ober principle. That according to the Ober principle, electron fill first in the lower energy atomic orbital before filling higher energy one. And then after that, you can go for the pairing of the electrons. So it is something 1s, 2s. Then it is like this. 1s, 2s. It's going like this. Energy wise. That means 3p, 4s, energy is having less rather than 3d. This is how these exceptions are there. So what Pauli exclusion principle tell us that no two electrons in the same atom have the same value for all quantum numbers. Suppose this is a orbital, you want to say in the here, if you are writing one electron like this, you can't write like this, another electron, same direction. You are saying that this is having plus half spin, this is also having plus half spin. It can't be possible. You have to represent electrons in an opposite direction. One is having plus half, another is having minus half spin. So, therefore, if the principal azimuthal and magnetic numbers, quantum numbers are the same for two electrons, they must have opposite spin. Okay, everything can be same, but spin should not be same. Hans rule says simple. It's saying that every orbital in a given subshell is singly occupied by the electron before a second electron is filled. Suppose if you are having 6 electrons, so then 1, 2, 3, 4, then 5, then 6. But it's wrong. You can't pair up it like this. This is already filled, this is already filled, it's fine. But in the p orbital, every orbital have same energy level. Px, Py and Pz. So if you want to put the 2 electrons, then you will say 1, 2. And if you want to put 3 electrons, then you will say 1, 2, 3. But if you want to say 4 electrons, then 1, 2, 3, and then 4, 6, 7, like this. So this is like how in the orbital that only contain 1 electron will have the same spin. So this is how we can say for the Hunt's rule. So this is something that arrangement of the electrons in the noble gas configuration that should know simply, because we are talking about the chemical bonding. So simple thing you should know. It's all about, we are talking about the basics. So you can check the rocket 2 plus 6, 8 electron, 2 plus 6, 8 electron, like this. 8, 8, 8. Every configuration is end up to octet rule. Now, when somebody is going to combine, like sodium is from the s orbital, sorry, you can say s block element. So it is having 1 electron in the outermost shell. So this 1 electron, it can easily give and converted into iron. So now this ion is getting stable. Why it is stable? Because now it is getting 2s2 2p6 configuration like this. But chlorine, they want one electron to complete the octet. See, 3s2 3p6 होना चाहिए था. So they can contain one electron. So Cl negative ion. So it is a non-metal and it is making anions. Sodium is a metal, so it is getting converted into cation. So this is how all chemistry of periodic table, gives you the important formation of the bonding. Now easily Na atom and Cl atom can easily be combined because sodium will convert into Na positive, Cl will convert into negative. Why? Because इसके पास एक्स्ट्रा इलेक्ट्रॉन है देने के लिए और इसके पास एक इलेक्ट्रॉन है लेने के लिए. So they are just sharing the electrons. So 3s electron of the sodium transfer to the 3p orbital of the chlorine. Similarly, in case of MgCl2, magnesium want 2 electrons to give, but these two chlorine atom want to take 2 electrons. So that's why एक इसको जाएगा और एक इसको जाएगा. So simple. So this is how we can, using Lewis theory, you can predict the chemical formula of the ionic compound. Okay, like CaCl. Okay, calcium is having 2, and how many electrons it can give? 2 electrons. So 2 chlorine atoms can combine. So it is a CaCl2. So Lewis formulas of the molecule show pattern of valence electron distribution of the molecule. It is useful for to understanding the bonding in many compounds. It allows us to predict the shape of the molecule and also to predict the properties of the molecules and how they are interacting with each other and making bonds. So this is how Lewis dot structure you can represent in the form of bonding also. See, boron is having 3 bonds. 0 lone pairs. Carbon is having, you can say, 4 bonds, 0 lone pair. This is having 1 lone pair, 3 bond pairs. This is also very important thing that to remember. So when you are writing the Lewis structure for a covalent molecules, first of all, you have to attach the atom together in a skeleton structure. Most of the metallic element generally central. Metal is central. Why is it so? Because metal is having electrons to donate. And halogens and hydrogen, they generally on the terminal. And many molecules tend to be symmetrical in oxyacetylene. So this is something all about that how we can calculate the total number of valence electron bonding. We can attach the atom with a pair of electron and subtract the electron from each used from the total. That bonding electron we can find out. It's no easy to say. Simply when you will go for your questions for the practice, then you will get to know about it. Okay. So if there are not even enough electrons there to complete the octet of the center atom, then bring the pair of electron from attached atom into share with the center atom until it has complete the octet. So this is how we can go for. So try, you can check here. If I go for this example first, HNO3. Here there is H, there is N, and this is oxygen. Then since oxy acid, H is on the outside, N is in the central, O is the other side. So N, we know that N is having 3 bond pairs, and it can be attached to easily oxygen. Oxygen having like this. So count the valence electron. We know that nitrogen is having valence electron 5, hydrogen is having electron 1. Okay, and O3 3.6. Total electron is 24 electron. O3 means every oxygen is having 6 electrons. You have to multiply by 3. Now it is getting 18. The total electrons we have 24. Now, how many getting used? Electrons. Start with the 24. Left with the 20. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are being used. Left How many left? Electrons are 16. इसका तो यूज हो गया. 4 इसके बचे हैं. 5 5 और 2 इसके लोन पेयर है. ये एक लोन पेयर इलेक्ट्रॉन्स. लोन पेयर कितने थे? 2 इलेक्ट्रॉन्स. तो हो गए ना. 5 + 5 + 4 + 2 उनके 16. So this is how we can explain our example. You can check it. Okay. So, but hydrogen is already complete with the 2. Now, I have already recount the electrons. You can see here this oxygen atom which are valence. They can be used as a double bond. Common bonding pattern for you have to go for as it can complete its octet. Here it is 1, 2, 3, 4, 5, 6, 7, and 8. You can represent it, but if you want to make these 2 electron like this, you can be use them. So these are the examples that you can go for. Okay, I'm slowing down this video. You can pause it and use this at home. Okay. Nitrogen tetrafluoride. Nitrogen trifluoride means nitrogen NF3 basically. NF3. N is less electronegative than fluorine, so you can put the N in the center and count the valence electron. N is having 5 electron and fluorine is having 7. Means 5 + 3 into 7. Why 3 into 7? Because 3 fluorine atoms are attached. First, second, and third. And you know what? Every fluorine atom is having 7 electrons. So how many? You have to draw it. How many you have to write it, and you can calculate. And we also can write the Lewis structure for the polyatomic ion. Sometimes it can happen that the procedure is the same. The only difference is just in counting the valence electron. For polyatomic cations, take away 1 electron from the total for each positive charge. And for polyatomic anion, add 1 electron to the total for each negative charge. So like this. NO3. Everything will be same, but 1 electron is added. 1 electron added. So here, this 1 electron, the 24 electrons, this is same. You can complete it like this. Representation will also be the same. Here to complete its octet, we have to transfer these electrons from here. So that means in NO3, there is a 1 double bond and 2 single bond. Okay, so same. I have already told you. You can draw this and you can draw the structure of CO3 to negative. Okay, so I will stop this video right here. In this video, we have talked about the Lewis dot structure, and I want to practice on it so that we can go for further types of bonding like ionic bond, covalent bond, everything. We will go for step by step. This will be our third part of chemical bonding, and I try to make it more simple so that you guys can understand the chemistry so behind it. And let's tune to my channel. I will be shortly coming with the my another video on the type of chemical bonding. Thank you guys. Thank you.